So good morning to all of you. I welcome to all the participants and our special guest, Professor Yuanbing Mao from Illinois Institute of Technology, Chicago. Professor Mao is an expert of designing the various nanostructures in different sizes and different shapes for measuring the size and shape dependent physical or the chemical properties. Professor Mao also has vast experience on electrochemical energy or electrochemical aspects of the hydrogen energy and the water splitting phenomena. Either it is the electrochemical, photochemical, or associated with some other means which we generally use in chemistry. And yesterday he spoke on very hot topic, how to design the nanostructures for energy, means energy materials. And today again he will speak on very burning topic, which is the hydrogen storage. And the hydrogen storage is not a simple problem, it is a very challenging problem. So today, not only the participants, the organizers will also be benefited from his expert talk on hydrogen storage. So with these words, I again welcome Professor Mao to please deliver his special lecture on hydrogen storage. Professor Mao, please.
Thank you, Dr. Ahmad, for the nice introduction. But the first thing I want to mention is, yesterday I mostly focused on, metal oxide nanomaterials, and but not today. Today it will be something different. So for the participants who ask me, why metal oxide nanomaterials are better, it's not depends on the applications. I do worked on some non-metal oxide materials. So that's what the topic today. So let's start. The hydrogen related to this is a term is called hydrogen economy. So the whole process is related to hydrogen, right? From here you can see that hydrogen can be generated by different processes. I will go through the details a little bit more. But here, I would just want to show you schematically with all these different ways, and then generate hydrogen, and then can be distributed, and then can be used. So why hydrogen is so useful is because it's high efficiency and reliability. Especially it has zero or near zero emission of greenhouse gases. So that's why people are so interested with it. Of course, when we say zero or near zero emission, that also depends on how hydrogen is generated, right? So 2 days ago, when I was talking about the photoelectrochemical water splitting, and that is really gave us a zero or near zero emission. But if we generate hydrogen from coal or distributed natural gases, this type of processes, it may not be. So that's one thing we also need to realize, right? So with that, let's move into it. Why hydrogen economy becomes popular. First is there are some issues with our current energy sectors. The first issue is because there is a limited supply of fossil fuels, even though some people also don't look at it in that way. But when we talk about the fossil fuels, right, including coal, oil, and natural gases. So the main important is the increased carbon dioxide content in the Earth's atmosphere. If you look at this this reading here, you actually can so clearly see, starting from 1955 to 2015, for example, right? That's about 60 years, and then we can see how much the carbon dioxide in atmosphere has increased, right? From about like 310 ppm to 400 ppm. So that's a quite increase, right? And then, other than that, right, there is a growing world population and then higher standard of living, right? Because we all want to live a higher standard. So that's, that's really generate a lot of needs for more energy, right? So the potential solution, one of the potential solutions is hydrogen, right? Because hydrogen is the most abundant element in the universe. Okay? It's not on the surface of the Earth, right? That's something we need to realize. Hydrogen has the highest energy content of any common fuel by weight. I will show you some figures on this. So we will understand it better when we compare with other type of fuels. And especially if we burn hydrogen, it will produce water, right? So that's an easy chemical reaction. So that's why, hydrogen becomes hydrogen economy becomes a potential solution. And then related to this is, one thing we need to realize is hydrogen is a secondary source of energy, right? So more specifically, hydrogen is energy carrier, similar to electricity. So it's not the energy source. So not the direct energy source. So that's one thing we also need to keep in mind. Though hydrogen, has the lowest energy content by volume when we compare with the gasoline, right? Here you can see that, when hydrogen is pressed to 10,000 psi, it has 4.4 millijoule per liter. When the liquid form is 8.4. But gasoline, just by itself, in normal conditions, is already 31.6, right? That's several times, higher than hydrogen, even under the 10,000 psi or in the liquid form, right? So, but the other important thing is the current production mostly is by electrolysis, which is expensive. If it's still reforming is cheap, but it generates a lot of greenhouse gases. So that's why, this is one thing we need to really look into this. That's why on the first slide I mentioned, when we say zero or near zero emission, it depends on how hydrogen is produced, right? Experimental production, for the electrolysis, biomass gasification, also in the experimental stage, it's not commercialized. So one day, hopefully, we can get to that, right? So hydrogen, there's another aspect, right? We talk about the hydrogen generation and the hydrogen storage I will show you some examples, but there is another thing is related to hydrogen delivery, right? Delivered to the users. So that's also one thing, we need to look into. For example, here shows like, we use a central wind electrolysis, generate hydrogen, and then compressed, and then go through the pipelines, and then the terminal for compressed gases, and then truck delivery, just like our gasoline, right? And then we will be able to use it, right? Here I use the one example, hydrogen fuel cells. I will show you more about this. So that's the full cycle of it, right? Then here, the one on the left, I'm showing, how we compare the gravimetric density of hydrogen compared with some other energy sources, and also the volumetric density. And you will see that, right? Hydrogen, if it's whether it's a liquid hydrogen or the different pressures, right? Hydrogen actually has pretty high gravimetric density, but then the volumetric density is pretty low. So that gave us, why people consider hydrogen, there is a hydrogen economy. So in 2010, for example, this figure shows actually US tried to use it for light-duty vehicles. And you can see that the cells actually, in certain years actually went very well, right? there are two, for some times, for some kind of the vehicles, in certain ranges, and then there are millions of units were sold. And then you can see the longer range vehicles being tested. So the data here is in 2010. There is a reason for that because right now the hydrogen-related storage is a bottleneck. So the U.S. government nowadays barely provide funding to this type of research. Of course, there are some countries, still have a lot of research going on this aspect, but not in U.S. now. Okay, so the results which I will show you was from several years ago when I had a grant on that, but not now. Okay, hopefully we will be able to get back on that. So in terms of the elements for hydrogen economy, right? There are different components. So the topic I mentioned, I will spend more time today is related to storage only, right? But this is not the only thing. Because I showed you earlier, right? There's the production, and there's delivery, and then how do we use it, right? Use the fuel cells, and then put the fuel cells in vehicles, then of course there's a technology validation as well. Safety, there's another thing, right? We all know that, right? Hydrogen is, it could be very dangerous, right? It's not even like a gasoline. Gasoline, we can smell it, right? Hydrogen, we cannot even smell it, we cannot see it, right? So safety is really, really an important thing. Of course, right? How do we use it? How do we packaging? So there are codes and the standards. Those are the things we need to be. These are the things that should be developed as well. And there is education as well, right? So how to make this forward? The hydrogen economy forward. Definitely, we need to educate the public and also the next generation, right? So this can be moved on. So it's a whole system like this, right? And then this figure shows actually the timeline of a hydrogen economy. So it should happen, in 2010, around 2010. So the R&D should be done, right? But around like 2015, right? And then then there should be commercialization decision, and then around 2020, right now it should transition to the marketplace, right? And then later on, there's a phase 3. It should be expansion of markets and the infrastructures, right? Because especially the delivery system, right? Then definitely we need a new type of infrastructure, not like the gasoline, right? We are using mostly right now. And then the phase 4 is realization of hydrogen economy. So the timeline is around 2040, right? So whether we can get to that, there's a big question mark. Okay. I will tell you why, the hydrogen related research is paused in US, just in a little bit. Okay, so as Dr. Ahmad already mentioned, this is a really challenge, really tough research topic, and that's why. And in recent years, there was not much progress, so that's why it's paused. So if we look at the whole process again, in terms of the hydrogen production, and I'm going back to this, right? Just in a different ways to show this, right? So let's look into each of these production processes listed here. Okay, the first one is the steam reformation of natural gas. So which is from here, so it is, as I mentioned earlier, is the cheapest method, right? Basically, methane and with water, and then it converted into CO and hydrogen. But then we need to see that this reaction happens at a quite high temperature, and also in the presence of the metal-based catalyst. Okay, and then for the CO, we can continue convert it to with the extra water, convert it to CO2 and get more hydrogen, right? But then definitely you see what is generated, right? CO2, which we need to consider the carbon capture, right? So, and that's one process. Then the other process is called the electrolysis. So basically, we electrolyze water into hydrogen and oxygen, right? So the energy here, is from electricity, and then there are different ways, right, to do that. So that's what it shows here, right? Where the electricity is generated, right? It can be from nuclear, it can be generated from coal, right? Actually, in US, the electricity generated by coal is more than 50%. That's why, the general public, we don't know where the electricity comes from. At the same time, we all, blame about the coal, right? It generated lead to the environmental issues, right? But then we use electricity generated by coal. And that's just a little bit of side story, side comment. And then, there are other ways to generate electricity, right? So from geothermal, wind, solar, photovoltaic, right? Those type of techniques. It just depends on how the electricity is generated, right? So that's why I said earlier, hydrogen is actually the hydrogen economy is not always zero or near zero emission. Depends on how the electricity was generated. And of course, this process, to make it faster, there are other ways, right, to use the high pressure, high temperature, and the catalyst, and then there's the gasification as well, right? The coal or the biomass converted into gaseous components by heat under pressure in the presence of the steam. And then again, this also need to have a carbon capture. And then in the later years, there's a new process was developed, which is called Raman process. Basically, we have the biomass or directly converted into carbon black and hydrogen. So from the carbon, whatever the carbohydrates, and it is in energy efficient. The pure 100% carbon and hydrogen. So it's of course, it also need a high energy input. Then there are biological processes as well. Some of the bacteria actually they can consume water in night or without light to produce hydrogen or the byproduct. So that's the other ways. So once we generated hydrogen, right? How do we use it? That's also right. How do we use it efficiently? Okay, more specifically, that's one thing, right? So basically, eventually, they all generate water, right? So hydrogen reacts with oxygen. Oxygen comes from air, and so that's why there are different type of fuel cells shown here. The most of the common ones we are familiar with is right here, right? With the membranes, photoelectric membrane fuel cells, right? But there are other type of fuel cells as well. And then, for example, the solid oxide fuel cells, and then they react at a much higher temperature, and so it's more efficient, and also there's no need of catalyst, right? Other than the electrolyte. So, but then, because of the high temperature, there's a much higher demand in terms of the properties of the components of the solid oxide fuel cells. And also because, when we start and when we turn it off, there's there's a time as well, right? For especially right when we want to start it, you need to reach that temperature, that takes time and generate a lot of the thermal stress on the components of the cells. So that's why each of these has their pros and cons. A lot of research are still going on this aspect. So that's something, if you would like to get into any of these fields, there's always interesting, but it's quite practical, so that's one thing you may consider. So then we talked about the hydrogen generation, and then how do we use them, right? So we miss one part, right? How do we store them, right? Because if we want to transport it from one place to another place, so we have to store it, right? And also, for us to use it in these fuel cells, and then we also need to store it first, right? And safely store it. That's very important. So there are different ways, for hydrogen storage. In general, people divide, categorize as a physical-based method and material-based method, so that's what, in general, people categorize them. In terms of a physical method, right? Basically, use the external pressure, so compress the gas, right? Or use the lower temperature, cold, cryo, compressed as well. And then, really at low temperature, we get liquid hydrogen, right? So each of these processes are not easy, right? We know that, these are higher pressure or lower temperature. So then the material-based methods, then there are different ones. Some of these are, it could be a physical process, physical adsorption process, or some of these are the chemical process. So I'll get into this a little bit more details. The currently commercialized vehicles actually use this physical-based method because this material-based method is not reached that level yet. And that's why a lot of research are still going on in this. If you are interested with this, and then you can find a solution to solve this, you will be famous and make a lot of money, right? that's one thing, So we will get into this different processes. There are different strategies, right? There are the absorbents. You probably heard about the MOFs. That's the monoaerial, and then the liquid organic. And then interstitial hydrides. So basically, these are the crystals, but because of this unique, alloys, and because of their unique elements, they can form hydrides, and that store the hydrogen there. And then there are complex hydrides as well. And then there are chemical hydrogen. You can see this molecule. The major part of is hydrogen. So of course, we need to consider whether this is a reversible process or not, right? That's the other thing. Okay. While some of these processes are reversible, and that's especially if we want to use it for vehicles, right? We hope it's a reversible process, right? So once we use it up, and then we can, just like we add gasoline for our vehicles, right? And also it should be fast. So to get it commercialized, there are a lot of technical challenges, not just about the content, how much we can store, right? And how fast, and how controllable it can be released. All those are the real, aspects we need to consider. But right now, mostly we mostly care about the how much we can store there and warm the water conditions. So here, this is what is the in terms of the capacity, okay, in terms of the hydrogen storage capacity. So here you can see that, these are some of the techniques I just showed you earlier. Compressed hydrogen, right? System capacity by weight, it's not that high, right? But it still works for vehicles, right? It's just make the vehicles much heavier, right? Or we need to it's go to it only can go shorter distance range, right? And then low temperature metal hydrides, it has good capacity by volume, right? But the capacity by weight is pretty low, right? From here you can see that the chemical storage is reasonably good. But it's still, the main important thing is it doesn't meet the DOE target, original DOE target. Okay, so the DOE target means if we can reach this target, then it's the hydrogen economy could be economic, right? But so far it hasn't really achieved that level yet. And so that's why, at least the US government, sees the funding support to continue this type of research in recent years. And hopefully, it will get back. So that's something really important. And the other thing about this figure is you will see that both of these horizontal and the vertical scales are logarithmic. So that's why, even though you see here, right, it's not, it looks like it's not too far away, right? But because these are the logs, so it's far away, okay? So then the other way we look into this is, as I mentioned, right, there are different methods, right? Mostly here, these are the physical method, then we go here, is more material-based and the chemical absorption processes. So the hydrogen density is actually, increased along this way, okay? But then, when hydrogen form bonds with the element, and then the hydrogen accessibility is more challenged. So that's why hydrogen accessibility is going to this way. It becomes easier and easier. Compressed, we can just release it quickly, right? And it's get accessible. So these are the two opposite ways, and then in terms of the hydrogen storage mechanisms, there are two mechanisms. One is called the dissociative chemisorption, and the other one is adsorption. So the adsorption is more physical or chemical. It could be physical and chemical adsorption, right? So the dissociative chemisorption is so it can dissociate hydrogen molecules into hydrogen. Okay, so that's what it means. It dissociate. So I will show you one example related to this, right? So it has a high hydrogen storage capacity, but because of this dissociation, you can imagine, right? So it has slow, in general, it has slow kinetics for obstruction, and it could be irreversible adsorption or desorption. Okay, so that's one thing we need to consider, right? And then the physical and the chemical adsorption, because it's only the regular adsorption, right? So it's fast, in terms of the kinetics. But then the thing is, especially for physical adsorption, we need low temperature because our hydrogen could be physically adsorbed on the surface, right? So at room temperature, it doesn't work well. Okay, at ambient pressure, it doesn't work well. So that's why, in this type of adsorption process, it normally happens at low temperature and high pressure. Okay, I'll show you a couple of examples which we did at the room temperature. And then, the low adsorption enthalpy, right? So those type of things. So especially, if we really want to look into this, these two mechanisms, you can see that, on this side is more related to the physical adsorption process. So you have materials with high surface area, okay, with a lot of pores, and then we will be able to store, we will be able to physical absorb hydrogen on the surface, right? So in general, right, the bonding between the hydrogen and the adsorbents are weak. So that's one thing. But that's also lead to the cryogenic operation temperature. Okay, and then on this side, this is in general use the metal hydrides, right? So hydrogen actually form bonds with the adsorbent. Okay, so there's a strong bonds formed. In between, it could have the adsorption on the internal surfaces, for example, the pores or the powder surfaces. So that's all the processes. And then, how do we get a higher surface area or smaller pores, right? So that's what we are going to talk about. The strategy we explored in the past is we use nanoporous materials. And also one technique I want to show you is, can we functionalize those nanopores? Okay, I will show you one strategy like that. Right, first we talk about when materials are at the nanoscale, right? They have distinct different properties than those observed in their bulk material counterparts. And then because of the small characteristic size of this nanostructured materials, and which will strongly influence the thermodynamic and the kinetics of hydrogen adsorption and also the dissociation, okay, by increasing the diffusion rate and also decrease the required diffusion length, right? So then what are the most important factors to determine the hydrogen uptake or the hydrogen storage? So that include the surface area, the pore volume, pore size, pore structure, and the surface treatment. Okay, I will talk a little bit more about the surface treatment. So the example I'm going to show you, the main innovation is by adjusting functionality of the nanoporous materials and modify the surface property and the pore sizes. So we can enhance the hydrogen storage capacity. Okay, so that's what I want to go into show you. So what we did, okay, for example, just imagine this is a porous silica materials. Okay, in general, you have hydroxy groups, and if we can use some of these silanes to functionalize the surface of this silicon, the porous silicon, right? So we thought, it could enhance the hydrogen adsorption capability. So why we consider, this type of organic molecules would help? Because those are the organic, those are the hydrophobic non-polar groups, okay? And then we know hydrogen is also non-polar, right? So that's why we believe, like we all know that, like dissolves like principle, right? So silica surface is not polar, right? So that's why we thought this could solve this problem. So yeah, so then for porous silica, we know that they are highly tunable, right? With nanopores, with different pore sizes. Depends on the structure directing agent, surfactant, for example, by copolymer, colloids, colloidal crystals as template, right? And then we can synthesize the porous oxides or carbons, right? With a specific pore size distribution, and then we can study the effect of hydrogen adsorption as a function of the pore size. So that's what I'm going to show you. And how did we do that, right? We know that when we want to make a porous silica, right? We use this TIAs, right? And when we add a surfactant, right, to tune the pores and the size, distribution, right, and the orientation, right? But here we add another silane, which is called TMS. The difference with this TIAs is other than this type of groups, there's a group with double bond, so it makes more non-polar, right? So we add all this together, depends on the amount of this compound. Okay, so that's the amount of the use X represented, and 0%, 10, 20, 31.5%. Okay, And then we just did the synthesis like this. And then we tested the hydrogen adsorption, hydrogen storage property of the compound. So for us to do that, we want to confirm that, this type of groups really, the linear Mason link groups really get into the porous silica, right? So how do we know that? So we use the FTIR, and we can see that there is a specific peak with the increasing amount of the VTMS, and then we can see this peak is getting stronger and stronger. So that tells us that so there is more VTMS in the formed porous materials, and we can move the template as well, right? Then we take X-ray diffraction patterns, and we can see those peaks are still here. The only thing is when we add more VTMS, and then the polar, actually the structure slowly changed. Eventually, it becomes more and more dissolved. That's why we added 31.5% as the maximum. We couldn't add more because if we add more, then the polar structure will be completely destroyed. Okay, so that's one thing. And then this is before we remove the template, right? And then this is the post, after we remove the template, and you will see the meso structure changed a little bit, right? And actually, if we really look, and we can see the meso structure is actually improved once we remove the template. Okay, there is a peak around 2 theta, around 6.9. This peak can be destroyed during the template remove process. So you can see here, after remove the template, this is not there anymore. And then, in terms of the size of the morphology of these particles, they are in the micro size, and as you can see here, so about 200 to 800 nanometers. There is a quite significant particle aggregation. So yeah, that's the other thing we can see here. But most importantly, we need to take the nitrogen adsorption isotherms. So you can see these different samples, actually these shapes are different, right? So there are a couple of things, right? For these two samples, okay, with 20% and 31% of VTMS, almost identical type 4 isotherms. So that represent these two plots you will see here. Okay, these are those two samples. But then for the other two sample, which is VTMS 0%, 10%, and then you will see that there is a change in terms of the slopes. That means actually initially it's saturated, and then subsequently with the further increase of the pressure, and they can absorb more nitrogen. Right here we use nitrogen, and this is the nitrogen adsorption isotherm. And also remember, okay, this is at the liquid nitrogen temperature. So based on this, we can calculate the pore size, the surface area, and you will see here. I'm not going to look into these figures, okay, but the data from this table is from this plots. So you will see that the surface area actually, initially increased, and then if we add too much VTMS, then it start to decrease, right? As I showed you earlier with the X-ray diffraction patterns, we can see that, right? The mesoporous structure actually start to destroy it. So that's why. Okay, so there's optimum amount of VTMS we can add into the synthesis. And then, here shows the pore volume and the pore width as well. You can see the samples here, in between is actually very nice numbers, right? Compared with the other samples. So that's the other thing from here. And then of course, right, the nitrogen adsorption isotherm basically, is to characterize this type of porous materials, right? But the goal here is we want to test the hydrogen adsorption isotherm, the capability, right? So this is what we did to take. We took these isotherms at again liquid nitrogen temperature. Okay, so for different samples, what we see is so the hydrogen adsorption capacity actually increased with the VTMS loading. So you will see that. So you see here that actually increase here, right? And then the weight percentage is actually, when the VTMS is 20%, 31.5% is actually the weight percentage is highest. It can reach 0.72%. Okay. While this, you will see there is a decrease there, right? So so that is because the structure changed. And then also we will see that there's a slight hysteresis. So that means there's some hydrogen is actually retained when the pressure lower, decreased. Okay. Yeah. So that's what we see. But the most important thing is you will see that this is at liquid nitrogen temperature. Even though the percentage showing here, 0.72% weight percentage is not too bad. This value is not bad. But one thing we need to realize is this is a liquid nitrogen. Okay. So that's pushed us to, so before we move on, okay, so to summarize this, right? So we use the linear trimethoxysilane to modify the hexagon mesoporous silica, and by using different amount of VTMS, okay, by co-condensation grafting strategy, right? We use the more than one loading percentages, and then we can see that with this different amount of VTMS, the hydrogen adsorption capacity actually increase with increasing VTMS loading. Okay, the maximum 0.72 weight percent absorption actually was achieved, right? So this is one way, right? The grafting basically happened during the synthesis, right? We also thought about, whether it could be possible to surface functionalize of those porous materials after the synthesis. So this is what this slide is showing about. So, we synthesize the mesoporous silica and then we functionalize it by this molecule. And we can see that, there is actually quite a big difference here. And then the maximum hydrogen uptake is reached 2.13 weight percent. Again, this was achieved at 77 K, right? So with that, we've been thinking about, right, whether there is a way we can store, hydrogen at least at the room temperature and ambient pressure, or maybe a little bit pressure. So there is one quite a unique way. It's called the spillover. So basically, it's a chemisorption process, right? So we have hydrogen comes in, and it go to the catalyst surface and get dissociated, and then it was dispersed on the surface of the adsorbent. Okay, so mostly the catalysts will be metals, right? Palladium, those type of noble metals, recently people been exploring non-noble metals. So this is what we schematically show you, right? The adsorbent, what could be a good adsorbent, right? Definitely we want to have something has high surface area. So that's why here, we try to use the graphene, functionize the graphene. So graphene is also something recently, right, becomes a hot, material. Some people say this is the model for graphite, right? It is, right? You think about the carbon nanotubes, right? You just need to roll it, right? So the most important thing is, the reduced graphene or oxidized graphene. So it has a lot of surface functional groups, right? On the surface or on the edges, right? Epoxy groups, the hydroxy groups and the carbonyl groups, those could be greatly useful for further functionalization, right? For by metals, by other groups, right? So that's why graphene could be nice. And here, in terms of the metals, we picked these different ones, palladium, is a good option, right? Because there were studies showing that the dissociative hydrogen absorption on palladium-111 surface, right? But then when we look at the periodical table, right, palladium is here, so it's close to nickel, cobalt, copper, right, silver as well. Yeah, we don't want to go to rhodium, right, because it's also too expensive. So that's why here, we chose the nickel and silver, right? So that's what we started with, and then what we did is, we start to making the graphene oxide, right, and then reduce it. We can reduce the graphene oxide by hydrogen, and then we also did, functionalize it, basically depart, functionalize it with metal particles. Right here, is functionalized with nickel, this one, and then we also went through the same process, right? It reduced the graphene oxide, and then this one, other than nickel, we also added silver, right? Yeah. So. Yeah, this is actually, I believe there's a typo here. Yeah. So, and then the other one is other than the nickel, silver, and palladium. So we got these three metals here, right, on the surface. And here we actually showed some electron microscope images, and then you can see that some of these are those nanoparticles on the surface. And we also confirmed by EDEX, with those metals on the surface. And we did XRD as well. And, by detailed analysis, we can see that, especially in this region, and then this is a zoom in, and you will see that, right? The palladium peak actually shift. This might be due to the, you will see that, right? This is maybe due to the substitution of the silver into it. Okay, and then if we look in this region, and then there are also some peaks. This part actually shows that this is related to this peak around this region. So the reduced graphene oxide actually showed a very broad peak around 2028, which indicate amorphous phase content. Okay. Okay. So this peak shows that, similar position for this hybrid samples, which means it has metals, right? And then if we look into this region, and then we will see there's a peak around 11 in the graphene oxide, right? But for the reduced graphene oxides, and then that peak is gone, okay? So why there's a peak for the graphene oxide is because there is an interlayer spacing, okay? But once it's reduced, then this peak is disappeared. That means it's reduced. So that's from the XRD, and we also did some other characterizations. For example, here we did the Raman, and you can see this D and G peaks, and also the 2D peaks for these samples. And then we measured, the intensity ratio of these samples, and you will see that the graphene oxide, this ratio is about 2.1, but then for the reduced ones, this value is lower. So that's consistent with the literature data. And then in terms of the XPS data, and then we can see that in these different regions, it shows that different carbon-carbon bonding and for carbon oxygen bonding. And then for the graphene oxide, you will see that, these three groups of peaks, right, coexist. But then for the reduced graphene oxide, basically this carbon oxygen double bond basically, it's almost disappeared. Okay, so that's also consistent because it's reduced. So there's less carbon and oxygen bonds. So and then we also did the XPS for some of these samples, right, to confirm they are metals in the samples, right? So here for this sample there's the nickel peaks, and then this one shows the nickel peaks, and then also the palladium peaks, right? At different binding energies, and then for this sample, then we saw nickel peaks, palladium peaks, and also silver peaks. So that also helps us confidently, about the samples, right? What are in the samples, and then we really characterize these samples, right? Here shows that the PET surface area, you will see that, right? So when the graphene oxide is reduced, actually the surface area increase because reduced graphene oxide, they are mostly curved, not like the graphene oxide, it's more flat, right? So and then for the hybrid RGOs, then those numbers get back to small values. That is because the extra step, so that decreases the surface area. And you can see the pore volumes, are more or less the same. And then we also did the hydrogen absorption, right? But the one thing I want to point it out is this was done at room temperature. Okay, that's different from the example I showed you before. So that's why this hydrogen, the weight percentage absorbed, is lower than the previous samples, right? But the most important thing is now this is the room temperature. So these values, especially for this sample, is actually quite decent. Okay, it's still small. Okay, we need to point it out. It's still small, but this is already demonstrated that we can use some cheap methods, for this purpose. We don't have to use the pure palladium, right? So that is related to this project. Okay, so then this sounds looks working, right? By the spillover mechanism. So then the thing is, we also consider, right? Then the sample we showed earlier, it takes a while to synthesize, right? And also the surface area, as I showed here, for the graphene oxide, for the reduced graphene oxide, this is actually not a high value, okay? At least based on the literature. So, I mean, we didn't try to optimize that, right? The purpose for this study is we want to show that these metal particles actually helps to improve the hydrogen absorption, right? So, so the next study we want to see is whether we can further increase the surface area of the graphene or the reduced graphene oxide, and also get the smaller particles, right? The particles I showed you, actually, they are quite big. So that led to this, next project. And here we chose the cobalt and for this study. And so we didn't add palladium. And so we initially were thinking, to use this to make it even cheaper. So that's what we did. So what is how do we do that, right? So if you like a popcorn, actually this process is quite similar, right? So again, we made the graphene oxide, right? And then add some salts, cobalt salts into it, and then we did the popping. So how do we do the popping is we use the microwave. Just heat it up, put it in the microwave for a couple of minutes, and then it will pop once it reaches a certain temperature, and then we get the samples. So this actually, this shows more details about that, right? The popping is actually happens around 178 degrees Celsius. So this is the initial pristine graphene oxide, right? So you don't see metal, cobalt in it. And then this sample is the cobalt doped graphene oxide. So you see cobalt peaks here, right, from the text data. So again, from the XRD, we see a peak here, so we know that, the samples are amorphous. So then again, we did the Raman, and then you will see that, these two samples, these values are quite close, right? So that's why these are the, so, and then for this one, we did, from the XPS, we did see the cobalt. So there are cobalt in the samples, right? And then again, we did the nitrogen isocene and also the hydrogen adsorption. And then this is at room temperature, this is at liquid hydrogen temperature. So we will see that, the pristine graphene oxide, has a good surface area, but then once we add cobalt into it, and then surface area decreased again. So that's still some improvement we should do there. And then in terms of the hydrogen adsorption by weight, this is the value we got, with cobalt there, this value increased almost double, right? I mean, more than doubled. The values here is lower than the previous sample with palladium. That's understandable, right? Here is just cobalt. I wish we did, add a palladium in the sample at that time. But that would make the data more comparable. But that's what we got, Then, one of the collaborators, actually, his group also used rice husks to make those porous materials, and then loaded with palladium. And then we did the hydrogen adsorption at 77K, and the values here is actually pretty decent, right? You see here is about 2.5. But again, this happens, the measurements was done at 77K. So that's the other thing, So with that, to conclude, I showed you a few examples. So the first one is that we use the hexagon with porous silicon and then functionalize it, right? And then we showed better performance of this functionalization, right? But anyway, the measurements was done at the liquid nitrogen temperature, right? And then later part, I showed you some examples about, the metallic particles decorated reduced graphene oxide samples, right? And then the result was taken at the room temperature and the ambient pressure. But still, we need to increase the surface area of the graphene. That will make it much better. But overall, there's still a long way to go before the goals set by DOE are met. So that's one thing. So, I mean, in terms of the future direction, if we can develop porous or the silica, use different modifiers, a template, while condensation strategy could be nice, right? And if we can functionalize different nanoporous materials using different silanes and modifiers, that also will be good. The spillover mechanism is actually quite promising, and which definitely deserves further investigation as well. Whereas carbon-based material derived from biomass for hydrogen storage could be explored as well. So those are the things, we could explore. Yeah, with that, then this is the knowledge I think I showed you in my previous presentation, so I will go through this quickly. So with that, if you have any questions and comments, yeah, please.
Thank you so much, Professor Mao. Dr. Ufana, now you can ask the questions on behalf of the participants. Dr. Ufana Riaz.
Yeah, I don't know.
Yes.
Maybe now hydrogen storage is not, not active research area.
Yeah, there are several questions, Professor Mao. It is in the chat
But I know, there are some studies, there are some research groups in like Japan, in Germany, and they are still working on this area. But in general, it's not as popular as like 10 years ago. And now I think most people, who work with porous materials are focusing on carbon dioxide capture. So.
Yeah.
So I'll take up the questions.
Yes,
yeah,
please, Dr. Ufana.
That's a general comment.
So the first question has two parts. The first part is, does introducing the alkene group increase the mesoporosity?
Oh, I cannot hear you.
Am I audible?
Now, yes.
Yeah, the question is, does introducing the alkene group increase the mesoporosity?
Let me see. In general, the porosity increase the porosity. So here, let me show you the data here. Yeah. So, it depends. It depends on the amount. Right here, you can see that. As you can see that, yes, it does increase. It does increase. Especially at a certain amount with DMS, the pore volume also increased. But then the pore width decreased. And that's also understandable, right? Because basically we add the ligands on the surface of those pores.
The second part of the question is, after the hydrogen adsorption, do we get to see any significant peak for SiOH in the FTIR?
After the hydrogen adsorption, let me see. We did show FTIR. That could be a interesting experiment to do. But we didn't have the facility to do that. You mean with the hydrogen in the porous materials? So yeah, unfortunately we didn't do that.
The next question is the pore diameter at 2.4 nanometer for the VMS system. For the VMS system, the pore diameter at 2.4 nanometer, isn't it an artifact value?
Why it could be an artifact value? Because the pores could be quite small.
So I guess it couldn't be an artifact, as they want to know about the artifact, whether it's an artifact value or a real value.
Yeah, so here, right, you see the pore width or the pore volume. Pore width is about a few nanometers, right? As we show here. Yeah, I mean, a few nanometers, that's reasonable, right? You know, those template molecules are about that size.
The other question is seen in the chat box, that porous silica versus MOF, which is best storage material. Are both materials electrochemically accessible electrode materials? Porous silica versus MOF. Are they electrochemically accessible electrode materials?
Oh, the MOF, right? Electrochemically accessible. Let me see how to answer that. Yeah, I mean, I think some of those. I remember, you know, I read some research papers about some MOFs. They are electrochemical active. I believe so. I'm not an expert on that. But you know, MOFs are you know, a lot of people are working on them, and recent days, yes, and they have been applied for different areas. You know, that's going to be something interesting if any of you are interested to work on that area.
Do silica-based materials tend to be more capacitive electrochemically? Thus, they have limited catalytic properties. So how can this problem be addressed? I mean, they are more capacitive electrochemically, all the silica materials, and therefore they have limited catalytic properties. So can we address this issue?
Yeah, I mean, you know, we use silica porous materials is silica is widely studied, right? You know, and they also easy to form high surface area porous materials. So that's why, you know, the studies we did here, you know, is based on silica. And then, you know, even later on, people try to make porous carbon materials. People use porous silica as a template. So there's a chemistry into it, and as I showed here, you know, this is actually based on silica, the phase diagram. But for other oxides or other materials, is difficult. I mean, you know, to achieve this type of control in terms of the pore size and the diameters. Yeah, I hope that answers your question.
Yeah, I think they're giving the response that they are happy, satisfied. Okay, the next question is, can we use COFs and MOFs for hydrogen storage?
I believe some studies, there are some reports on that. Yeah. And as I showed later on, right, especially, you know, the MOFs or the GOFs, you know, if there are some metal centers in those materials, right, that can act as a activation site. So, yeah, it's just I recent years I didn't work on, you know, I haven't worked on this area, you know, in recent few years. So I have a kind of yeah, detached from that. Yeah, that's a good question.
I guess these are the only questions that we have, and
Yes.
no more. And
Yes.
I guess the participants are satisfied now with the queries, and they're very happy. They're very enthusiastic with the presentation. Thank you, sir. Thank you, Professor Mao, for a wonderful presentation. I mean, this has kept
Thank you.
all the participants really intact, and they've been continuously posting questions, and they are very happy to, discuss the issue and come up with some good remedies which could help in designing MOFs and COFs with good energy storage capability. So it has been a wonderful discussion today, and very different from yesterday's, and it was really good. I mean, kind of you to, spare so much time on covering so many wide aspects of energy storage materials, and every lecture, gives a different and beautiful insight and keeps us really, glued to the system, just to see those beautiful graphical presentations that you've shown and the data. So I guess with this, I hand over it to Professor Tokeer for
Thank you, and thanks everyone.
Yeah, thank you, Professor Mao, for very exciting talk on hydrogen storage. It was really very, very informative, and I enjoyed your whole lecture. Every content was very useful, and definitely all the participants will use in future too. Thank you so much, sir, for being with us. And tomorrow we will meet at 10 o'clock for a grand lecture, and tomorrow we will have only yours lecture. So thank you so much.
Look forward to that. Yeah. Thank you.